You can broadly categorize aviation's climate impact into CO2 and non-CO2. So CO2, we know, is driven by fuel burn. And the primary non-CO2 effect is this type of artificial cirrus cloud warming. And that's, I think, not really, in the public awareness.
Welcome to Growing Impact, a podcast by the Institute of Energy and the Environment at Penn State. Each month, Growing Impact explores the projects of Penn State researchers who are solving some of the world's most challenging energy and environmental issues. Each project has been funded through a seed grant program that's facilitated through IEE. I'm your host, Kevin Slyman. Contrails, the cloud-like streaks left in the sky by jets, are the effect of water vapor condensing around soot and dust in the atmosphere. These artificial clouds from the aviation industry contribute to climate change, and that impact is likely to grow as the number of air travelers is anticipated to grow significantly in the coming decades. Additionally, the airline industry's efforts to address climate change may not be adequate to properly keep pace with the need. On this episode of Growing Impact, a team of researchers discusses the climate challenges associated with aviation and the team's efforts to mitigate the climate impacts of contrails. Hello, everyone. Thank you so much for being on Growing Impact today. Could we go around and have everyone introduce themselves, tell us your name, and a bit about your research?
Sure. Good morning. Thanks for having us here. And my name is Sven Schmitz. I'm the Boeing Welliver Professor of Aerospace Engineering, teaching at the undergraduate and graduate level here in fundamental and applied aerodynamics. My group also conducts research in the aerodynamics of current and future aircraft, propulsion systems, wind turbines, and helicopters.
My name's Andrew Carlton. I'm a Professor Emeritus of Geography. My specialty is physical geography and climatology in particular. I'm also a Penn State Academy professor. And most of my research over the many years I've been doing it has been focused on regional and larger scale climate processes. And I've actually been looking at contrails, studying them in some form or another for about the past 40 years, almost 40 years.
And Borji, could I pass it to you for your introduction, please?
Yes, I am an assistant professor at Penn State Abington near the Philadelphia region. I am teaching engineering and physics classes here, and my research in around the material science, defect properties of the materials and the radiation of the material properties. And I also recently interested in sustainability in education, and that's, I think, where I come from in this project.
My name is Guido Cervone. I'm a professor in geography, meteorology, and atmospheric science here at Penn State. I joined Penn State in 2014, so I'm close to my 10 years anniversary in just a few more months. My expertise is in geoinformatics and remote sensing. I'm a computer scientist by training, and I have a very strong appetite for large data and analyzing those large data primarily to detect anomalies or to make predictions. And I privilege problems that are either extreme or rare. And I built my career on analyzing data relative to natural hazards or renewable energy.
Your project is investigating contrails and their impact on climate. And for those who may not know, contrails are those cloud-like streaks that are created by jets in the sky. And before we get too far into contrails, can we discuss aviation's overall impact on climate?
Well, yeah, first off, to start with a number, I think currently aviation's impact on climate change is estimated at about 4%. So you may get the reaction, hey, that's not all that much. So now comes the big but here, right? And the big but is that the passengers are supposed to increase fourfold in the next 30 years. So we're getting a 4 times increase here. And then climate impact of aviation has been a little bit dormant compared to other climate impactors. And while those are already working on it in reducing their climate impact, aviation has been growing exponentially, and that topic has been somewhat a little bit neglected. Also to the absence of really scientific insight into the processes of how aviation impacts climate.
Yes, and I think in terms of the impacts on the environment, I think these can probably be grouped into two main areas. One is of course, the emissions of the various gases, such as carbon dioxide and water vapor. Also the soot particles, the particulates, and then also on the other side is the generation of these high altitude clouds, these trails that we call contrails. And so between those two aspects is really where you have the major impacts on the atmospheric environment. At least, and I guess as we'll talk about, there's also from that impacts on the surface environment in terms of temperature, for example.
People in the industry of aviation, they are aware of this situation, that it's affecting the environment, it's affecting sustainability, and they are producing new solutions. This might be new fuels or new engines that might reduce these contrails, but there has not been a study or investigation on, are these solutions really sustainable from the life that it has been beginning to the end of these production of new materials or new engines or new fuels. Are they really sustainable? That's another question.
Can you discuss the challenges that the airline industry and airlines themselves face in bringing on new and more efficient jets, and maybe the components within those jets?
It takes decades to develop a new aircraft and to certify it. Right, so keep in mind you're moving hundreds of people in one aircraft across the ocean. So the certification process of that is very intense, and the cost is immense. Now there is no revolution in sight, but it has been a constant evolution. Engines have been improving. Right, they're now twice as efficient, meaning they burn half the fuel compared to 25 or 30 years ago. You see things like winglets. These are the edges at the tip of the wings, and they have various shapes. So there is active research that has been going on to upgrade existing aircraft. So again, there has been an evolution, but these improvements, they have not been able to keep up with the general growth of passenger miles in aviation. An interesting number to note is that 50% of all flights are done by 1% of the people on Earth. 80% of the flights are done by 2% of the people. So we have a world where also, and you mentioned it before, more and more populations want to travel, and they are all good sides with traveling and meeting and interconnectivity of all sorts. But it's a challenging topic.
Can you define what a contrail is?
Yes, a contrail really is an artificial cloud. Contrail stands for condensation trail, implying that this cloud that forms behind the jet engines of aircraft is the result of condensation of water vapor around soot and dust particles in the atmosphere. And although we've called them contrails for a very long time, it's probably more accurate to refer to them as ice trails or sublimation trails, because they are composed of ice. Because they form in the upper levels of the atmosphere, or what we call the troposphere, where it's very, very cold. The water vapor tends to sublimate into ice rather than into water vapor, though you can get them at lower altitudes from planes in lower altitudes where there will be water, liquid water as well as ice. But anyway, these long trails will form not behind every plane because sometimes the atmosphere is too dry. It can be cold, but it may not be cold enough, and it may be too dry. And if you do not have enough moisture in the upper troposphere, you may get a contrail that lasts fairly briefly. It'll be a short trail, and as you watch it from the ground, you can see the trail just following the plane but disappearing shortly after that. But when you have enough water vapor in the upper troposphere, and when it's cold enough, then you can get these what we call persisting contrails. So these are the contrails that will spread across, or at least the linear clouds will spread across the sky or reach across the sky. And because they require certain humidity and temperature conditions, if you're in an area where there's a lot of aircraft flight, jet engine flights, then you can sometimes see these multiple trails across the sky. And over time, and by that we mean probably beyond about 40 to 60 minutes, if the conditions are still suitable, these trails can spread and become thinner in the vertical sense. They can become thinner, they can spread laterally across the sky, they can merge with other contrails, and then we call them contrail cirrus. And it's contrail cirrus that is really has the potential to have the biggest climate impact, because they tend to act more like a bit more like regular cirrus clouds, natural cirrus clouds, than artificial clouds. And again, the coverage that they get across the sky has the potential to increase their impacts.
To confirm, you're saying naturally occurring clouds affect climate, correct?
Yes, they do. Okay. And yes, it depends on the kinds of clouds that you have. Probably most climate scientists would agree that lower level clouds, or thick clouds in the lower levels of the atmosphere that are comprised more of water, liquid water, and maybe with some mix of ice, tend to have a bit of a cooling effect on the Earth's surface, because they tend to be more reflective of the incoming solar energy than they are to trap the heat that the Earth gives off, the infrared or long wave radiation. But as model studies have suggested, and even observational studies, if climate change involves increases in upper clouds, cirrus level clouds more, that has the potential to make greenhouse gas warming or amplify it, make it worse, by letting solar radiation still pass through during the daytime, but also having the heat trapping effect. So yes, to answer your question, different kinds of clouds, natural clouds, do have an impact on climate, and they have the potential impact on climate change, depending on whether the increases are at lower levels to middle levels versus upper levels. Contrails do differ from natural clouds, even though they're both upper level cirrus type clouds, and this affects their impacts on the climate a bit, the surface temperature. The contrail clouds tend to have smaller ice particles in them than natural cirrus clouds do, and also they tend to have more of these ice particles in a smaller volume. And so those two things together tend to make contrails, at least when they initially form behind a jet aircraft, it tends to make them a bit more reflective of solar radiation than natural cirrus clouds do. Natural cirrus clouds tend to have somewhat bigger ice particles, and there are not so many per unit volume. But again, as contrails spread over time, they tend to resemble natural cirrus clouds more and tend to have similar kinds of impacts.
I think a lot of folks are familiar with CO2 or carbon dioxide being a contributor to climate change from burning fossil fuels. However, there's non-CO2 warming. Can we discuss what non-CO2 warming is?
So I think you can broadly categorize aviation's climate impact into CO2 and non-CO2. So CO2 we know is driven by fuel burn, and the primary non-CO2 effect is this type of artificial cirrus cloud warming that Andrew just explained, and that's I think not really. In the public awareness that half of aviation's climate impact is really caused by these non-CO2. And that also includes, nitrate oxides and water itself, which is a greenhouse gas, into the upper atmosphere. So it's this balance of non-CO2 where there's also a large uncertainty bar in the climate models of what the particular effect is. I don't know, Andrew, you probably know more. As I understand that, I mean, that effect is as old as the Earth.
Right. Yes, and it's again related to as the temperature increases, you tend to get more evaporation, and when you get more evaporation, you put more water vapor into the atmosphere, and then you tend to increase the temperature, and it can be something of a positive feedback, and we see that in our own lives. I think when we if you have a humid night, a night in which there's a lot of water vapor around, it feels humid, the temperatures tend not to drop as much as if you have a night, let's say at the same time of the year, but where it's very dry, the atmosphere is very dry, there's very little water vapor. You tend to have the overnight temperatures tend to drop lower. So that's a way in our everyday lives that we can see that impact of water vapor on sustaining temperature and maybe even amplifying it.
I just wanted to contribute to the discussion by looking at it maybe from a different angle. So think about the Earth as a system that must balance its energy. So, and the energy comes primarily from the sun. There is, a little bit of energy self-created, like internal tectonics and magma and so on. And then there is infinitesimally small comes from the moon and from, the stars. So most of the energy, comes from the sun. And all those different, unfortunately, we have an atmosphere, because if we didn't have an atmosphere, the equator would be a lot warmer than it is, and the poles would be a lot cooler. So, effectively, the atmosphere is one way to redistribute this energy from this excess of energy at the equator to towards the pole. And it does that at different time scales. We have ocean currents that redistribute energy in 50 to 100 years. And then, we have regular atmospheric circulations that do that, time scales of days to months. And then, we have extreme events, things like hurricanes that they're a very efficient way to redistribute energy in, a few days. And if you think all those hurricanes, they form over, almost equatorial areas, and then, they dissipate, at higher latitudes. So they just redistribute energy. Now, all those gases in the atmosphere, things, let's say just water vapor and clouds in general, they are part of this balancing mechanism. Because in a sense, they change the albedo of our planet. So with albedo, we basically, you can think of it as the color of our planet. Of course, it would be integrated over the whole electromagnetic spectrum, not just the visible. But basically, the clouds, they are helping to either reflect some of the radiation from the sun that you'd actually reach the surface, from preventing from doing so. But then it will also help, the long wave radiation, so basically the heat that, the Earth is generating, just reflecting it back. And, clouds are a very important way that they help that Earth has to balance this energy. You can imagine that, if we start increasing, artificially, those clouds, we're basically tampering with the Earth's natural way to balance its energy.
When it comes to Contrails, what are you exploring, and can you tell us about the goals of the project?
Project is titled A Multidisciplinary Approach to Mitigating Climate Impacts of Aviation Contrails. So that's really what we're after. So one challenge has been, how do you cover in predictions, in models, that disparate range of timescales? And so here, right in my area, I think that gets approached by doing high fidelity simulations of complete aircraft with engines and work on the contrail formation. And then I thought I need to work with somebody who has kind of a Earth system point of view, which is a geographer. And so I first met Andrew and convinced him. He was just retired, to meet for coffee with me, and he was surprisingly interested in sharing his career insights into Contrail. And then we also involved Guido and Bourgeois and Masa from the Abington campus on the sustainability aspect. Yeah, so what we are really aiming is bridging the gap between a short-term simulation and then sort of verifying and validating that with its longer-term impact through satellite imaging. So I'm an aerodynamicist on this side, and I pass it on to Andrew and Guido now for the geography side, and we circle into Bourgeois for the sustainability side.
Yes, so my work on the project relates more to the detection of the contrails and using the satellite data, and so identifying them, determining their characteristics, and relating those to the atmospheric environments in which they occur. And at least that's sort of the bigger picture. And then from that, can we extrapolate forward? How is climate change, for example, going to change those upper atmosphere environments? Will that potentially increase or decrease contrail incidents? And obviously that's separate from the role that changes in jet engines, changes in aircraft may do. So there is a predictive aspect there, and a link to the model verification. So we do need the observational analyses to in their own right, but also to link in with model verification. And I think Guido can probably speak more specifically to those kinds of things.
As Andrew just said, I'm also interested in the use of remote sensing to detect the clouds, primarily from a computational point of view. So, now that we know how we can detect the clouds, how can we build a system that can do this at scale, basically over the entire planet every few minutes, and so something that is efficient, so that it won't take a few hours to detect the clouds on let's say a few minutes basis. And then another aspect that I'm quite interested is, can we assimilate data from the airplanes, data that Andrew pointed to us that are available? How can we try to link the environmental data that are detected from the airplanes with the formation or not of contrails that we detect from the satellites? And then finally, the last aspect that I find extremely interesting is, how do we link this to models, both the atmospheric models? In other words, are the atmospheric models doing, so the atmospheric models, they generally do not simulate clouds, but can we actually use the output of the atmospheric models in order to estimate when contrail clouds are most likely to form or not? So even though the models do not output contrail clouds, can we actually do that? And the second is, how do we get all this knowledge that now we have gathered into the engineering model, where we actually have the formation of a contrail or not?
From my perspective, me and my undergraduate students, we are conducting life cycle assessments for future aviation technologies that we have. Basically, let me first tell you what is a life cycle assessment. It's a systematic analysis of an environmental impact on a product during its life cycle. This starts from manufacturing to end of the life. Earlier, you had a question, is recycling of jets or jet engines, is it really worthwhile? That's something actually we can simulate and we can see the cost efficiency. We are using CAD programs, computer-aided drawing programs. Either our students are simulating the jet engines, or they already get the jet engines. We have some parameters that they can play with it. For example, materials, they can try different materials. If we use a different material than they are currently using, can we reduce the impact on the environment, negative impact on the environment, or can we reduce the cost? Does it really worthwhile to recycle the material, or can we change the manufacturing methods? Does the transportation matter in the environmental impact, considering where it's manufactured and where it's shipped to be used? We are investigating all these effects and trying to find out this new technology's effect on the environment.
Yeah, and our ultimate goal is really to take here the next step and look at both, right, anticipated improvements in engines and new aircraft configurations, right, aircraft that are more of a blended wing body, and use other engine technologies and addition, hybrid electric propulsion, boundary layer ingestion, and these type of stuff, and see how those affect the formation and the evolution of the contrail into a contrail cirrus and its ultimate optical depth and net radiative forcing. So we are getting the data and the models together, and we are ready for the next step. And as you mentioned, yes, it's a big challenge, but this team here with its background everybody here can play with their own strengths. Mm-hmm. To work on this. It's an exciting one, and it's something different. I'm not aware of any group inside or outside Penn State with that unique mix of expertise to tackle that problem.
Sven, just a moment ago, you talked about, or you mentioned net radiative forcing. Could we talk a little bit about it and talk about how its relation to the work?
We have radiation coming to Earth, and we have radiation going away. So the main incident part is coming from the sun, and then what irradiates from the Earth is at different ranges of wavelengths, and so clouds and greenhouse gases play an important factor here. And the net balance of everything going in and out is what really defines net radiative forcing.
Different clouds, different levels of clouds and thicknesses of clouds have different impacts on that, what we call the cloud radiative forcing. So lower and middle level clouds tend to be thicker. They tend to have more liquid water in them and less ice. And so they tend to be more reflective. They tend to reflect more of that solar radiation than they trap the long wave heat energy being given off by the Earth. So as a general statement, they tend to cool the Earth's surface. But contrails and natural cirrus tend to be different. They tend to be thinner. They tend to be ice, as we've already talked about. And so they if you think of it in terms, let's say, a layer of cirrus or a contrail layer, there are sort of holes, if you like, in between the ice crystals that let through more of that solar radiation than most other clouds would at lower levels and that have more water. So they still tend, and we see that on a day in which there may be a lot of cirrus cloud around, it's still quite bright outside. There's a lot of solar radiation still coming through. There's not all that much being reflected away. And at nighttime in particular, the presence of these cirrus clouds can also trap some of that heat energy. So cirrus clouds and contrails are no different in this respect. tend to have a positive net radiative forcing. They tend to warm the Earth's surface, whereas natural clouds tend to have a negative net radiative forcing. So in terms of climate change, models tell us different things, but we don't really know. Are the high clouds going to be increasing in the future more than the low level and middle level clouds, or will it be the opposite? Because that will determine, to an extent, the rate of increase of the surface temperature, even separate from continued greenhouse gas emissions.
If we implement solutions, can aviation be a sustainable form of travel?
I think the answer is, well, probably not, never, right? And we have to be realistic about that and deal with that answer. I just started reading this month's National Geographic, and the editor-in-chief comments that, yes, travel has a complicated relationship with sustainability, even for the National Geographic that sends out explorers. So to become carbon neutral and sustainable is utopia. But I think a realistic figure is to consider something like a carbon neutral growth. That means we are projecting a four-fold increase in passengers in aviation, but we want to curb the additional carbon and non-CO2 effects to a level, say, right before the pandemic in early 2020. So even though everything increases, we stay at a carbon neutral growth. And that's probably a realistic figure here. Half of that will probably come from sustainable aviation fuels of some sort. The other half, a mix of yet another aircraft technology improvement and operational improvements. Now, the thing with Contrails is, as a concluding remark, it affects all three of them. The aircraft technology in the engine, the operational improvements around susceptible areas in some form, and then with sustainable aviation fuels that have different components of nitrate oxides and soot.
I just want to maybe make a little bit optimistic comment on the sustainability part, because like my other part of research on the material science part, and now seeing that there's this new materials produced, and then like not just in the aviation, also in the spacecraft. That's another thing that I'm working on. Like, can I have a material that can work good with the radiations and all these impacts with the space? And from my studies, I can say that it seems optimistic to me with these new materials. I guess it's just a matter of getting more funding towards this area, making this research a little bit faster so that we can make these materials in the industrial sizes. I think that's the biggest challenge. And I can tell that we have done preliminary simulations with the existing jet engines, and we have seen that mostly the materials and the manufacturing has the most effect on the environment, most negative effect. So that brings the question that there are two things that we need to change. One of them is the material, the other one is the manufacturing method. And as I mentioned, in terms of material, I'm very optimistic. And in terms of manufacturing, also, we are seeing that even in these days, in the aviations, there are these 3D printed parts of the plane that may not be applicable to the engine, but the other parts of the plane that makes a little bit more sustainable.
Well, to the question you posed about what the environmental impacts if we do nothing, then what we can expect really, of course, is to see more of the same. And what is that more of the same? Well, that is that in areas of high density of air traffic, where there's a lot of commercial aircraft flights. We've seen over the last 50 or so, maybe 60 years or so, increases in regional cloud cover due to contrails. We've seen decreases in what we call the diurnal temperature range, which is the difference between the daily high temperature and the typically overnight minimum air temperature. And those are consistent with the impacts of high-level clouds on the surface temperature. And so particularly in places like Western Europe, or Europe in general, actually, and the United States, we've seen some of those biggest decreases in the daily temperature range and increases in the cloud amount. And in certain other areas, we believe that, or some studies have shown that there's a change in the local evaporation rates as well. If you have more high clouds, then you tend to have a little bit less evaporation from the surface. And if you have less evaporation from the surface, that can change the temperatures in the horizontal across spatial scales, and maybe even change pressure, surface pressure, and even local winds. So those last things are not yet demonstrated so much as argued on physical principles. But again, if we do nothing, we're just going to be having more greenhouse gases emitted from jet engines, particularly in areas of high density of air traffic, and more contrail clouds and their impacts on the climate near the Earth's surface where people live.
I really want to thank you. Thank you, Sven, Andrew, Borju, and Guido. Thank you so much. I really appreciate you taking time.
Absolutely. Thank you.
This has been Season 4, Episode 4 of Growing Impact. Thanks again to Sven Schmitz, Andrew Carlton, Borju Austin, and Guido Cervone for speaking with me about their research. To read the transcript from this episode and to learn more about the research team, visit iee.psu.edu/podcast. Once you're there, you'll find previous podcast episodes, related graphics, and so much more. Join me again next month as we continue our exploration of Penn State research and its growing impact. Thanks for listening.